Okay, everyone, it looks like it's about 7 o'clock now, so I want to kick things off and get started. So over the last week, we talked about some basic stack smashing, so how we could overflow buffers, how we could get a buffer overflow, and we could overwrite other data on the stack, including variables, and especially including other kind of function metadata, if you will. So when I say function metadata, I'm mainly referring to return addresses, which means that we can jump to any arbitrary code. We can jump to any function, and we can execute that function. And we also talked about shellcoding a little bit, which is a really basic way that we can inject our own code into a program. So if there isn't a function that does exactly what we want to do, we can very easily inject our own code with shellcoding, and we can make our program do whatever we want it to. So those are two really, really cool techniques. However, unfortunately, the sands of time are unrelenting, and so we unfortunately, or fortunately I suppose, have mitigations in place to stop both of those things. And so I want to talk today specifically about the mitigations against stack smashing, so stack cookies, as well as mitigations against shellcoding that have been developed. So we're going to kick things off. We're going to get started talking about stack smashing and stack cookies, which are a mitigation to stop those. But first of all, because this is INTROSEC, I want to make sure that everyone's on the same page. I want to kind of slow down and review a little bit of how stack smashing works. Basically, the fundamental idea is that we have some program like this, where we have some buffer of data, some array here of fixed length, and then we just get data into it. We can get data through any number of functions. Right here we're using gets, which, as we talked about last Monday, is a really, really dangerous function. But this can also be something like scanf. This can be fgets. Basically anything that you can get input with, you can potentially trigger an input or an overflow with. And so this function here on the right, we've drawn out what the stack frame is going to look like, what the stack is going to look like here. We're going to have some kind of space on the stack for the local variable here, in this case for that stir variable. And then you're going to have another local variable, in that case that's going to be x. And then you get to the interesting stuff. So right here we have an EBP, so we have a previous base pointer that we've saved on the stack, so that we can pop that and we can point back to the previous section of the stack whenever we want to, so whenever the function returns. And then kind of by that same logic, we have a previous instruction pointer as well, and so that's going to be the address that we return to. That's going to be the address of the code that we jump back to. So if we put too much data in, instead of filling up this buffer of fixed length, we're going to be overflowing into other variables and eventually into the saved base pointer and instruction pointer. So as we can see here, once we put too many A's in, we fill up all of these variables, these slots, if you will, with A's, which is in hex, a capital A like this, is going to be OX41. So in here, we can see the stack after we've just thrown a bunch of A's in, we've overflowed into the return address. And then things get really interesting when we're able to take that return address, and instead of putting, just a bunch of A's in or a bunch of garbage like that, we're able to actually point that to some other section of code. So right here, we have the return address, which we've somehow made point to this win function. And so that win function is going to be executed when this program returns instead of the actual function that called foo. So that's a really, really quick overview of how stack smashing works. We've talked about that a couple of times now. I just want to make sure that we can really make that information very concrete for everyone. But basically, a stack cookie is going to be a compiler mitigation that will prevent a lot of these stack-based buffer overflows from being exploitable. And the way that it does that is it inserts some kind of cookie, or sometimes it's called a stack canary, into the stack. And it's kind of like the tale of the canary in the coal mine there, where as soon as there's some kind of trouble going on, as soon as something goes wrong, that canary is going to get killed before any of the interesting return addresses or base pointers that we keep on the stack. So that's going to be kind of an early warning system for us. And so on a 32-bit system, the way that this is going to be implemented is it's actually going to have a 4-byte stack cookie. So that's going to be 32 bits on a 32-bit system. And as you can imagine, on a 64-bit system, the size of each one of these slots, if you will, is going to be 8 bytes. So we're going to have an 8-byte stack cookie. And because this stack cookie, or this stack canary, is between the local variables down here and the function metadata, so that base pointer and the return address, as soon as the local variables get overflown, that stack cookie is going to be modified before an attacker can modify anything interesting up here, anything that they could do malicious things with, potentially. And of course, that doesn't do us any good unless we also check that stack cookie. And so when an attacker does overflow into the return address, and they do overflow that stack cookie's value is going to be checked right before the function returns. So before that return instruction is executed, and before the function will actually jump back and pop that return address into the instruction pointer, it's going to look back at the stack and it's going to say, is this the value that I set it to before? And if not, it's just going to abort. So at the end of that function, it's actually going to call this special function called stack check fail if it does not line up exactly with the stack cookie that it put on the stack before. And what stack check fail does is it prints out this warning message to the user, and then it just aborts the program. It quits it immediately. So if you've ever been working on data structures homework or anything like that, and you've seen that message about like stack smashing detected, that's what's happening under the hood, is you've accidentally overwritten some kind of stack cookie, and the program is going to be checking that stack cookie before it returns, and when it does return, or right before it returns, it's going to check that, see that it doesn't line up, and then call stack check fail, which will print out that warning about stack smashing detected. And so I wanted to walk you through the basic implementation really quickly, and I'm actually going to do that in a nice disassembler in Binary Ninja here, because I think that's going to be a little bit easier to see than trying to walk through on the slides. But this is the same exact binary that I've been looking at, that I put the screenshots on the slides. So we can see the start of this function, which has been compiled with a stack cookie, is going to look exactly the same as the ones that we were looking at before. It's going to look very, very similar. We're basically taking this return address, we're putting it on the stack, we're pushing the base pointer, and then we move basically move the stack pointer into the base pointer there, and then we start setting up local variables here on the stack. However, one instruction that looks really, really interesting that the keen-eyed among you might have picked up on is this instruction where we're moving something at GS OX14 into the EAX register, and then we're moving that value. We can see here we've moved it into the EAX register. We're moving the EAX register into EBP-OXC, and then we XOR it out. So if we remember from last week's talks, when we XOR a value with itself, it's going to be 0 at the end of that. And so this is something that we haven't really seen before. We haven't seen these 3 instructions at all in our previous exploration of binaries. The reason for that is these 3 instructions are setting up a cookie on that stack. So we're taking some value from this GS segment at offset OX14, and we're moving that onto the stack. And so that is going to line up with the position in the stack that's going to be between the local variables and the interesting function metadata, like the return address and the base pointer. And then we zero it out so that at no point later on in the code can we just look at that EAX register and see exactly what the stack cookie is. Because as you can imagine, and we'll talk about this a little bit more later on, but as you can imagine, if you can leak that stack cookie, if you can somehow figure out what value that is, none of this does any good. Because you can just overwrite the stack cookie with the value that it was before and then keep it going. And that's going to undo all of the hard work of setting up the stack cookie and checking it at the end of the function's execution. So that's the implementation of the function prologue and how it starts how it sets up this stack cookie. But I also want to show you the epilogue, and again, I'm just going to do this right here in Binary Ninja, so it's a little bit more interactive and hopefully a little bit easier to see. So again, at the start, it looks pretty standard. It looks like exactly what we're expecting. We're modifying ESPs, we're basically tearing down that stack frame, and then we move 0 into EAX. And if we remember, EAX is usually the return address of a function. So if we're at the end of a function, we're moving a value into EAX, or it's not the return address, it's the return value. I'm sorry, I misspoke there. If we're moving a value into EAX at the end of a function, we know that that's probably the return value. However, these next 3 instructions are where things get really interesting, because we're going to be reading something off the stack. If we remember, if we look up here from before, EBP minus OXC, that's going to be where we moved, where we placed that cookie before, that value that we read from GSOX14. So we're going to be recovering that variable from the stack, and then we're going to be subtracting that. We're going to be subtracting what the original value was. We're going to be reading out of GSOX14 again, and we're going to be subtracting that from the value we have stored on the stack. So as you can imagine, we're kind of expecting this to be 0. If everything has gone according to plan, this is going to be 0, because those 2 values will be exactly the same. But if something's gone wrong and that value has changed at all, that means that the cookie has been corrupted somehow. And so we check that with a jump equal to, which if we remember from previous lectures, we will know that that jump equal to instruction is going to check the 0 flag. So if that 0 flag is set, so if this value, this difference is 0, then we jump down here, and we're going to be basically just popping the base pointer, tearing down the stack frame, and returning. So that's going to be a standard execution. That's going to be standard function prologue. However, or function epilogue, I should say. However, if that value is not 0, if that difference is not 0, then we're going to call this stack check fail function. And I told you a little bit about that stack check fail function before. Basically what that is going to do is it's just going to print out a message about stack smashing detected. So I can actually show you real quick that we will see something like that. We'll see that message if we just input a ton of A's. So right here, this is going to be enough A's that we can overflow that buffer. And when we overflow that buffer, we're going to corrupt that cookie. So I've printed out the value of the cookie. So before execution, before we get that data, that value is going to be OXFF, etc., etc., etc. Interestingly, there is a null byte here in the cookie, and that's very standard to make it harder to leak the cookie out. But that's a topic for another day. So after the execution, if we remember, a capital A in hexadecimal is going to be OX41. So after execution, this cookie will be OX41414141, and that obviously does not line up with the value that it is expecting. So when it subtracts that stored value from the value on the stack, that stack check is going to fail, and it will print out that message and then terminate the program. So that's a little bit about stack smashing and the most common mitigation against it. We talked a little bit about how that mitigation works, and we also talked about some of the flaws in that mitigation. So obviously, if you can somehow leak that that stack cookie, then it does no good for us. We can just overwrite that value on the stack with the value that it is expecting, and we can carry on with our nefarious schemes. And so we know that in this execution and in all executions, there's going to be a null byte in it. And because we're on a 32-bit system, that means that the entire cookie is 32 bits. It's going to be 4 bytes. And then one entire byte is all zeros, and that's a known value, which means that essentially there's only 3 bytes or 24 bits that are unknown to us. And so on a 32-bit system, a 28-bit brute force is actually completely within the realm of possibility. And so if you have a way that you can just keep restarting this system, you can just have this binary restarting. So oftentimes you see this in like a forking web server or something like that. It's completely within the realm of possibility to just brute force that and just keep trying values, keep trying random bytes until it finally lines up and it finally works. And so that's another common way to get around stack cookies, at least on a 32-bit system, which is what we've been focusing on for this series of lectures, is just brute forcing it and just guessing it until it works out. Now, the other kind of attack that we've talked about is shellcoding and how we can actually use shellcode to inject machine code into a binary, into memory, and then jump to that machine code. So I want to give a quick review. Maybe some of you couldn't make it to last week's talk, or maybe you just want another review to help make that information really concrete in your head. And then we'll be doing the same kind of thing where we're talking a little bit about the mitigation for shellcoding. Interestingly enough, if you'll note here on the slides, I have made some comment here about how this mitigation isn't like fully a mitigation for stack smashing, because there are a lot of ways around it. Unfortunately, we don't really have as many ways around the mitigation that exists for shellcoding, and we'll be talking about that a little bit later on. So first off, I just wanted to review a little bit about memory segments. Basically, when your program is loaded into memory, it has a lot of different segments here. So there's the .text segment, which is where your program's code is going to live. There's RO data, which is read-only data, and then there's data, which is read-write. There's the heap, there's the stack, and then there's other libraries. So libc is probably the most common one that we'll see. And so these are all loaded into different chunks of memory. They're all loaded at different addresses. And so that's something that we want to be keeping in mind while we're talking about this mitigation. There's these different segments of memory, and they each store kind of a different type of data. And then obviously we also want to do a quick recap of how shellcoding works. Basically, the principle is really, really straightforward. It's just that instead of sending input to this program, so in the case of the binary we were looking at a couple of minutes ago, instead of sending our name, we send in just raw machine code as our input. So instead of sending in like, hello, my name is Jeff, we would be sending in, my name is OXBB48F631, etc. And that's going to be the raw machine code that we want to execute at the end of the day. And then we were just talking a little bit about how we could overwrite return addresses, and we could jump to any functions that we wanted to. Well, we do that same exact trick. We just kind of pretend that this machine code is a function, and we just jump to it and we start executing that machine code. So that's a really, really high-level overview of how shellcoding works. Now let's dive in and start talking about the mitigation. This mitigation is called data execution prevention, or DEP. Sometimes it's also called W caret X, that's W exclusive or X, or NX. That stands for non-executable, or the WX there, the W's or X stands for read, exclusive, or execute. And the basic idea here is actually really similar to how Unix file permissions work. So some of you may be familiar with this already, but for those of you who are not, on a Unix system, so on Linux or on Mac OS or BSD or anything like that, you're going to have kind of 3 categories, 3 bits that you can set for every file. And you can say, can the owner read this? Can the owner write this? Can the owner execute this? And then the same for the group and for all other users on the system. So the important thing to keep in mind here is you can kind of separate how a user can access this file. So you can say, for example, my user can only read this file, or it can read and write to this file, but it can't execute it. Or it can read and execute, but it can't write. And the idea of data execution prevention, as the name would imply, is we prevent that execution of data, so of user data. So anything like this heap or the stack, where we know that's only really going to be used for like scratch space, for the user to input data into. There's no reason why we should ever have to execute data on these in these data segments, or in these memory segments that are used to hold data. And so we kind of take this same idea of a read bit, a write bit, and an execute bit, and we apply it to each individual segment here. So we know the .text segment, for example, that's used to hold program code. So you need to be able to execute that, and you also need to be able to read it so that you know what to execute. However, there's no reason that you should ever have to write to this .text segment. You should never be able to modify the code that's being executed. Similarly, on the heap or the stack, you should only be able to read and to write. You should never be able to execute. So that X bit should never be set when the write bit is set. So that's where that W exclusive or X comes in. That's where that no execute comes in. And interestingly enough, this is actually one of those things that has hardware support these days. So on a modern computer, you can set it up so that these pages, these memory segments, can only be read and executed, but there's no way that you can possibly in software, like even if you hack the kernel, even if you hack the operating system, there's no way that you can make this memory segment writable and executable. And so this is a much more concrete mitigation because it's really hard to undo it. That being said, not every system utilizes this. Not every system has hardware support for it even. And so this is one of those things that on something like a router, for example, it's really common to have an underpowered computer that doesn't have support for these fancy security mitigations. And so oftentimes if you're hacking like a router or any kind of embedded device, a lot of these memory protections that we're talking about right now just don't apply, because it's basically like the software is still running on a little tiny underpowered computer from the 90s. And so oftentimes when people are taking modern binary exploitation, which is a class that is now offered here at RPI, we get to the point in the semester where we talk about shellcoding, and we talk about this mitigation. They're like, oh no, why did we spend the last week learning about this thing that doesn't matter? Well, it turns out it does matter. It makes a lot of sense to learn about this so that A, you're prepared to go after these targets, and you're prepared to understand how these systems work, but also it puts a lot of the things that are talked about later into more context. And so with that in mind, I kind of want to be hinting a little bit. I want to be giving a bit of a teaser for Friday's talk, because we've effectively killed shellcoding here. We've effectively killed our only way of injecting our own code into the system. And so Friday, we'll be talking about a more modern way to do that. We'll be talking about a method that, to this day, on most mainstream operating systems, unless you go out of your way to prevent it, most programs are actually still going to be vulnerable to this method of code injection. And so with that in mind, I think that's all I have for you today. So I will see you on Friday.